Good evening. This is a presentation and a demonstration of the advanced sensitivity function of the Requs AI Predict software. This feature is an additional add-on to the Requs AI Predict machine learning software reliability prediction tool. This feature allows you to perform trade-offs between cost and scope and test efforts and corrective action time. The first thing we'll do is press the advanced sensitivity button. And you can see, still coming up. You can see there is a listing there of a few development factors. These are the development factors that received a negative or a non-affirmative response in the survey tab. So basically these are the gaps in development, and they are in ranked order. You can see there are really not too many here. And so what we can do, we can sort these by, in order to minimize defect density, or to minimize relative costs, or to minimize startup time. I have it sorted by minimizing defect density. So I'm going to click one. I'm going to click the design explicitly discusses faults and warnings. And I'm going to see what happens when I click that. So previously, the predicted defect density was 0.4088. And when I click that development practice, you can see now it's down to 0.4017. So there was a reduction there. It may seem like a small one, but it depends on how big our software is. If we have a multi-million line of code software system, this could have a pretty big effect that just by implementing one development factor. But these are all things we have to look at. We look at the relative cost there. The relative impact is relatively high here, not the highest, but it's up there. For just one development factor, that was quite a decrease. The relative cost is from 1 to 4, where 1's the lowest and 4 is the highest. It's slightly above low. What we see though is the relative time there, we see a 4. And the reason is that a lot of people it takes a little bit of culture change. This is really not an expensive thing to do, but a lot of people push back on it. A lot of software engineers don't want to do it. They'd rather write code than think about fault management. And so we could take a little culture change. It's not expensive, but just to get all the people on board might take a little bit of calendar time. So we can balance the defect reduction of this against the uphill battle of possibly getting people to do this development practice. We could also uncheck it and it'll go back to where it was, and we can click on another one, and we can continue this analysis until we find a development practice that we feel like we can live with, that we can implement quickly, and that gives a good reduction of defect density. Okay, let's look at our interactive analysis here. Okay, the interactive analysis is it allows us to do an even higher level sensitivity analysis. The previous tab gave us a means for which to do sensitivity analysis with the defect density, which is shown on the first slider. But we can also balance the other inputs. The effective size is how much code, how much stuff, how many features are being deployed. We can do sensitivity analysis with that. We can also do trade-offs with how many corrective action hours we have available for both during development and in operation. We could do sensitivity analysis with the cycle time. The cycle time is how many months per sprint or per release or per increment. And then we can also do sensitivity analysis with the test hours. Now you'll see the red lines in the blue areas. That's what's currently set in the software. Those are the default, those are not the defaults, but they're what we currently have predicted. So we can adjust these either one at a time or several at a time to optimize the escape defects we see in the second graph there. We have our initial analysis on the left. Then we can do our sensitivity analysis. It'll show up in the middle graph. And also the third graph is basically a graph intended to show us the percentage of defects that will be found before deployment versus after. So that orange line, it shows us where the deployment is predicted to be based on the inputs we've entered in. And finally, the pie chart shows us the percentage of defects that will be found in test but not fixed, found in test and fixed, found in operation but not fixed, and found in operation and fixed. So let's take one. Let's change our defect density and move it down. We're just going to move it down a little bit and see what happens. And you can see immediately the escape defects graph, the y-axis is getting smaller. And then let's look and see when we, somewhere around there, whatever I just recently touched, around 0.116, somewhere in there. Oops, yeah, right around there, 0.16. You can see the third graph really changed. That's because that defect density got down small enough to where it's predicted the organizations with that small of a defect density, they're deploying a little later. So that's why the bar moved out, the deployment bar moved out, and we can see a large number of defects now are being found earlier. So that was the sweet spot there for getting most of the defects out before deployment. Let's look at what happens if we double the size and have more product. You can see in the middle, it's basically going to double the defects. So doubling the size is about the same effect as doubling the defect density. They're both linear inputs. We could try cutting the size in half. You'll see what it does there. It simply has a linear relationship. Okay, let's reset our changes there, and let's go on and look at the cycle time. We have a cycle time now of 12 months. That's pretty long. Let's see what happens if we cut that down to 4 months. And meaning a release every 4 months instead of one release once a year. And if we're going to have a release every 4 months, we have to have a third of the stuff. We can't release the same amount. So we're going to knock this down about 1/3 the size. There we go. And you can see the effect is, a lot of people think this will have a purely linear effect. It really does not. If we look here, the predicted escape defects, even though we're developing exactly the same amount of functionality with exactly the same defect density, the plateau for the escape defects is actually lower. It was at 5 for the initial analysis, if you look over here. And we can see this bar over here. All we did was move the cycle time, and you can see the bar is now further to the right for deployment. And so this is basically the basis for having incremental development. It's just mathematically shown here. All right, so let's see what happens when we increase our corrective action time. Right now we're showing no defects corrected. I have an input of 8 hours per fault correction time. We'll just leave that where it is as a default. Let's see how many hours we need. If you look at the pie chart here, it shows found and test not fixed, 91%. Obviously, we don't want that. We don't want fixing no defects. Let's see how many hours we need to have during the cycle to reach about 75%. We want that orange area to be around 75%. Let's see where this will take us. Ooh. All right, well, somewhere at around 1,100 hours of corrective action time. So if you divide that by 8, that'll give you how many corrective action days in a 4-month cycle. we would need to deploy the software with actually 75% of the defects fixed, which is, it sounds like it's a low number, but it's actually a very stable place to deploy the software on most systems. All right, so that's interesting. But we've got all of our defects found in operation is not fixed. So let's see what we can do to address that. Oh, there we go. We would like for there to be as much white in that pie chart as possible, but not so much that we'd have too much. So let's see the point of which we, all right, looks like around, right around, not a little bit more than 100 hours, about 130 hours for corrective action time in the field. That's not a bad place to be. That means really 130 divided by 8 days to support the software once in the field. That's not much at all compared to the 1100. So we can do different scenario analysis with this to really come up with an optimal solution that optimizes the amount of functionality that gets deployed, the number of corrective action hours that we need to do out in the field and during tests, and so forth. And so thank you very much. That's the end of this presentation.